This is a continuation of our chapter on electrochemistry. We have reviewed how to balance redox reactions, and so now we're going to talk about some of the applications that electrochemical or redox reactions have. And one of the most common one is the use of batteries. So I'll walk you through these step by step, but in general, any type of battery involves a redox reaction where electrons are transferred from one substance to another substance. And in the meantime, for spontaneous redox reactions, there is energy released, and we harness that energy in the form of batteries. Spontaneous electrochemical reactions, spontaneous redox reactions, are known as Voltaic cells, also sometimes called galvanic cells. And so when I say spontaneous redox reaction, that's just as any spontaneous reaction is going to release a form of energy. And a redox reaction is going to release electrical energy. And so all batteries are spontaneous redox reactions. And so this is, if you were to do this reaction in a lab, the setup might look like this. Batteries are a little more sophisticated, but you have what we call two cells or two half reactions, and one of the cells is undergoing oxidation, the other is going reduction, and a wire is used to connect the two cells. The wire is the conducting substance that allows the electrons to transfer from the oxidation half reaction. Remember, oxidation, Leo says GR, so lose electron, oxidize. So whatever's being oxidized is going to be releasing electrons, and the side that's being reduced is going to receive or gain the electrons. So just as I used a mnemonic, a memory trick for what's oxidized and what's reduced, Leo says GR, I continue to use mnemonics throughout the redox chapter. So if we are talking about a spontaneous redox reaction or a voltaic cell, oxidation will always occur at the anode. Okay, so NOx. Reduction will always occur at the cathode. Okay, red cat. So an ox chased a red cat. So if you can get that visual into your head, the nice red cat here, you will remember what happens where. So let's look at an example. That always helps, right? So if we have a redox reaction between zinc metal and copper cation, and so they're essentially going to switch places. Right, so that's what's going on in this cell here, in this electrochemical cell. So the zinc is being oxidized, right? It's losing electrons. So the zinc is in the oxidation half cell because it's losing electrons, and oxidation happens at the anode, and so zinc is the anode. The electrons are traveling through the wire that's connecting the two cells, and the copper cation is accepting the electrons delivered from the anode, and so copper serves as the cathode. Okay, that's copper's but what's being reduced. And so notice that it is the copper cation that is accepting electrons to become copper metal, right? And it is the zinc neutral metal, when it loses electrons, turns into the zinc electrolyte, the zinc cation. Some more mnemonics for you. Electrons therefore always travel from the anode, where oxidation is taking place, to the cathode, where reduction is taking place. And my little memory trick again, A comes before C in the alphabet, right? So starts at anode and goes to cathode. A comes before C. That's the direction of electron flow always. Now, what drives, what makes a redox reaction spontaneous or not? It's the difference in reduction potential, which we'll talk about later. It's a difference in reduction potential between the two electrodes. Now, the electrodes are the actual pieces of metal in each half cell. So the difference in reduction potential between zinc and copper in this example. Now, one other thing I want to introduce at this point is as soon as even one electron is transferred from the anode to the cathode, we are leaving behind a positive charge in the anode, right? Positive charge is building up as electrons are leaving, and a negative charge is starting to build up in the cathode, right? And we know, hopefully, in nature that charge buildup is not good. It's not stable. The reaction would stop very quickly as the charge builds up. So to keep a spontaneous redox or voltaic cell going, or our battery going, we need something called a salt bridge. And the salt bridge balances the charge. The salt bridge balances the charge. So I just said the negative charge will be building up in the cathode as electrons are delivered. And so to neutralize that built up negative charge, the salt bridge has in it just how it's described, salt. And so the cations that are in this salt bridge will automatically start going into the cathode. It's an automatic draw out of the salt bridge. And because we have a positive charge building up in the anode as the electrons leave, anions from the salt bridge will automatically be delivered to the anode to neutralize the built-up positive charge. It's going to take over you to kind of iron this out. There's a lot going on. So again, the salt bridge contains a salt, which is unreactive. You can't pick any old salt. It's got to be salt that's not going to interfere with the reaction taking place. It's got to be soluble in water, right? Because most of these are aqueous solution. And here's your mnemonic for the slide. Cations move toward the cathode. Anions move towards the anode, right? So anions, negatively charged ions, move into the anode. Anode, remembers where oxidation takes place. And there's positive charge building up here. Cations move into the cathode to neutralize the charge. All right, so you know the basics of a voltaic cell. There is a shorthand notation that is commonly used for voltaic cells or galvanic cells. And so it's pretty simple. But the cathode and the anode are shown on the outside of the symbol notation for a voltaic cell. And just as we start with the anode because that's where the electrons start, right? And then ending up the shorthand is whatever the cathode is. States of matter are shown, okay? The anode and cathode, the pieces, the electrodes are always solid, well, not always metals, but typically they're definitely always solid chunks of something, very commonly metal. All right, and then in between the two, the anode and the cathode, we have the electrolyte solution. So the electrodes are immersed in electrolytes, aqueous electrolyte solutions. Now, just to remind you, what is an electrolyte? We learned that a couple units ago. Electrolyte is anything that conducts electricity. So in solution, what that requires are freely moving ions. So just to remind you of that. Any solution that has freely moving ions will conduct electricity. And so, again, these are things that are soluble in water, they're ions, so they are electrolytes. So the electrolyte solution, and it's very common to have the anode, cathode in an electrolyte solution of itself. Okay, so zinc is the anode, and the electrolyte solution in the anode half cell is the cation of zinc. here, same with copper. And then typically also in the cell notation, in addition to the states of matter, typically the electrolyte concentration of the electrolyte solutions are also included. So just to make sure that you understand the chemistry that is going on, I'm going to write the overall redox reaction that is going on. So we have learned in balancing redox reactions to break them into the oxidation half reaction and the reduction half reaction. So let's kind of follow along and see what happens. So you can think of some of the zinc atoms in the anode. Zinc is the actual anode, giving up an electron. And this electron that it gives up travels through the wire that's connecting the two half cells, and what's left behind is the zinc cation, right? The 2 electrons it gives up. So the zinc cation is left behind. Zinc cation is no longer a solid metal, so it falls off and becomes part of the electrolyte solution. And so you can imagine the mass of the anode is going to decrease. Okay, the solid anode is going to be turning into an electrolyte solution, more of the electrolyte solution. So that explains the oxidation half reaction. Then the electrons get delivered to the oxidation half cell, the cathode. But of course, they're not going to combine. Neutral copper doesn't want extra electrons. So they will combine with the electrolyte solution in the cathode half cell. And in this case, the electrolyte solution is copper cation. And so it's the copper cation in the electrolyte solutions that are going to combine with the 2 electrons from a zinc atom to make neutral copper. Once you have gone from the copper cation to neutral copper, it is no longer soluble in water, and as a matter of fact will plate out on the copper electrode, the copper cathode. And so the mass of the cathode will increase over time because you have copper cation, which starts out in the electrolyte solution, turning into copper metal, which is plating out or sticking to the cathode piece of metal. So the mass of a cathode will increase over time, and the mass of the anode will decrease. So here's an expansion. I talked to you before about an ox chases a red cat. Well, if you want to remember which one picks up mass and which one loses mass, this may help you. An anorexic ox chases a fat red cat. What am I talking about? All right. What I'm talking about is oxidation occurs at the anode, and the anode loses mass. It's anorexic. All right. Reduction, fat red cat, reduction occurs at the cathode, cat, and the cathode gains mass. That's why it's fat. Okay, so maybe look at this picture at the skinny old ox and the big fat red cat, and it may help you with a few of the multiple choice questions. All right, so now let's talk about what type of redox reactions are spontaneous and make voltaic cells and which ones are not. I mentioned early in this PowerPoint that it is the potential, the difference in potential between the 2 electrodes, the cathode and the anode, that determines whether or not it's spontaneous and how much electrical energy will be generated with this reaction. So the difference in the cell potential is referred to often as electromotive force, or EMF, just so that you're familiar with the terminology. That provides the driving force. Cell potential is more what you would see from chemists. and the units of measure for that are volts. I don't think you're going to run into joules per coulomb, but just in case you do, so it won't throw you, a little bit unusual. There we go. A little bit unusual units there in terminology. Now this is important to understand. We use a voltmeter. Probably most of you have at least seen one, to tell us the potential or the difference in potential between two things. If we get a positive reading on the voltmeter, that is a spontaneous reaction. Okay, so you got to be a little bit careful because with our signs, of course, we all know that from thermochemistry. And as a quick reminder, for example, delta G and delta H are energetically favorable when they have a negative sign, and delta S is energetically favorable with a positive sign. So it's important, and you need to review thermochemistry anyway, right? So we have delta S now has a friend. We know that to be thermodynamically favorable, we want change in entropy to be positive, and now we can add to that cell potential, that we want that to be positive, to be energetically favorable. So a negative, you put a voltmeter and it gives you a negative value, that's a non-spontaneous reaction. For the standard reduction tables that we will use to determine whether or not any redox reaction is spontaneous or not, this is not necessarily something you need to know, but I just want you to know where those values come from. Any substance, mysterious substance M, any metal that we want to test, we hook it up in a cell with what we call the standard hydrogen electrode and measure its potential relative to the hydrogen half cell, and so that's where the numbers we're using come from. So here's a sample standard reduction potential table. It is made up of substances all being reduced. Remember what reduction means. It means it's gaining electrons. And so you'll notice all of these are written gaining electrons. And it tells you the voltage, which will lead to energy, required for that substance to be reduced. And so remember now that a positive value for reduction is favorable, and a negative value is unfavorable. So as soon as you see a standard reduction potential that's negative, that means it is energetically unfavorable. So all of the substance at the top of this chart are readily reduced. Okay, it's energetically favorable for them to be reduced. All of the substances at the bottom of this chart they don't want to be reduced. They don't want to gain electrons. It is not energetically favorable. And what that means is that all of these substances at the bottom are readily oxidized. If something doesn't want to be reduced, that means it wants to be oxidized. It wants to give up or give away electrons and become a cation. Notice, and you may or may not remember this from previous units, if you remember our periodic trends, so as far as ionization, metals tend to have low ionization energies. They become cations. They tend to give up electrons and become cations. And you see that in the standard reduction tables here too. See all your metals down here, a lot of the metals down there. And so what we'll be doing is looking at the difference in reduction potentials between two different substances to determine if a redox reaction between the two of them would be spontaneous or not. The formula for a redox reaction determining whether it's spontaneous. Now again, remember that you want the overall difference in reduction potential to be a positive value if it's spontaneous. So the formula we use for determining that is shown here. So take a look, because there are different formats of it again, and I don't want you to get confused by the different formats. So basically it's saying whatever the reduction potential is for the cathode. Remember, how do you identify cathode? You'll see examples. But an ox chased a red cat, right? So cathode is undergoing reduction. It's gaining electrons, so you're going to get the standard reduction potential from whatever is being reduced in a reaction, and you're going to subtract from that the standard reduction potential for the substance at the anode. In other words, whatever is being oxidized, NOx. Now, you're welcome to use this formula. I find it, and students tend to find it somewhat confusing, so I have modified it, and this is the form I choose to use. It doesn't matter to me which one you will, but let me explain why. There's logic here. If you look back at any standard reduction table, you will notice, just a reminder, all of the half reactions written in that table are written as a reduction. If you have a redox reaction, not everything's reduced, right? You're going to have some substance that is reduced, but you're going to have another substance that is oxidized. But because the standard reduction table shows everything as being reduced, you are going to have to flip or reverse whatever substance is going to prefer to be oxidized, and those are the ones with a negative sign in that table. You're going to flip or reverse, which means you also need to change the sign. So let me just say, let's look at the sample we used throughout this PowerPoint. We had zinc combining with the copper cation, and the spontaneous reaction had zinc becoming a cation and copper getting reduced to the neutral metal. So if you wanted to find the overall cell potential for this reaction, you would find zinc being reduced on the table, but then you would look at this reaction and say, wait a minute, zinc is not reduced in this reaction, it is oxidized, right? It's losing electrons. So you would take whatever the reduction potential was in the standard reduction table, and you would change the sign of it. Okay, so it's probably negative, and I'm not going to go back now, but if you look at zinc in the standard reduction table, it doesn't want to be reduced, so it has probably got a negative sign in that table. But in this case, it was in fact oxidized, so we're going to change the sign. And then copper is what is being reduced, and so we're going to use the number right off the standard reduction table for copper. So bottom line, real quick. So that's all I'm doing here. So to use this formula, instead of memorizing where the negative is or isn't, all we're going to be doing is taking the standard reduction potential from the chart. Whatever's being oxidized, we're going to change the sign of its standard reduction potential in the table, and then just add those two together. So we'll do some examples. So let's look at this one, the zinc and copper one again. Here's the overall redox reaction balanced. Okay, again, zinc is being oxidized. So if you go back to the table of standard reduction potentials, the table that shows up in the table, or the value that shows up in the table, is negative 0.76. That is the potential for reducing the cation of tin. But zinc, but zinc is being oxidized. So we have to change this from the reduction potential. We have to reverse the sign, so it now becomes positive, and then also reverse the reaction to show what zinc really does in this reaction, that zinc in fact gets oxidized. So you will always have to reverse the reaction and the sign for any redox reaction. For whatever's been oxidized, it needs to be flipped. Now, since the copper in this reaction is in fact reduced, you can keep the half reaction written simply as it was written in the standard reduction table, and the value for the reduction potential just as it was in the table. Once you have the standard reduction potentials for each of the half cells. Simply add them, once you have their signs correct, just add them together. And that's it. And that is the standard E cell reduction potential.